So yeah, let's recap the first part of the fundamental theorem of calculus real quick. So the fundamental theorem of calculus part 1, basically there was some requirements that need to be true about continuity and stuff like that. But essentially, as long as your function's continuous, then what you have is that if you take the derivative of an integral from some constant to x of a function f of t with respect to t. Remember, the fundamental theorem of calculus part 1 said that this was just equal to f of x, right? You just basically take this x and plug it in here. This derivative and this integral essentially cancel out, right? You can kind of think of it that way. And so this is basically the first part of the fundamental theorem of calculus. The next thing that we had talked about was, okay, but what if, so we did some examples. So we did an example where we found the derivative of the integral from 3 to x of cosine e to the t squared dt. And we found that this was cosine e to the x squared, right? But then we did an example where we found the derivative of the integral from 0 to x squared of the square root of 1 plus t cubed dt. And we had said that this was equal to the square root of 1 plus t cubed. Nope, sorry, I started writing down the wrong line. It was the square root of 1 plus x squared cubed. And then I had multiplied it by 2x. And what I'm going to explain where this 2x came from, because I feel like last time I didn't do that great of an example or that great of an explanation. But essentially, if I kind of go back up and I compare this to this, so if I, what is happening? If I look at the derivative of the integral from some constant to some function now, rather than having x, I still have f of t dt in here. Well, what this is going to equal now is, so since I have x here, and then that's essentially what I put inside, what I'm going to have is basically now I have an inside function. So what does that kind of make you think of when I have an inside function here? That's now going to be my new input, right? So whatever is your limit, or whatever is like your upper limit, is what you're going to put inside. But so what kind of rule, when it comes to taking derivatives, would you think of when I start talking about like inside versus outside functions? Yeah, the chain rule, right? And so that's where this 2x came from, is because when you have f of g of x, you need to multiply it by the derivative of what's on the inside. And so that's where that 2x came from. So does that kind of make more sense as to why we were getting derivatives after doing all of these things? Okay. So I'm going to erase these examples. These are in the last notes. I think the first one was part A and the second one was part C of an example that we had done. But so yeah, and then here, let me just make a note. So this is just the chain rule where g of x is the inside function. Okay, so hopefully that kind of clears up those examples for you. But so let's continue this. Let's do one more example with this. So example, if we're told that capital B of x is equal to the integral from -6 to x squared of cosine of t squared dt, they want us to find the second derivative of capital B. So to find the second derivative, I should probably start by finding the first derivative. So what is my first derivative going to be here? I know I'm definitely going to have cosine, but what's what goes inside cosine now? Yeah, it's going to be x to the fourth because you would take your x squared and you would plug it in for t. And so you're going to have x squared squared, which gives you x to the fourth. But then now you need to multiply by the derivative of x squared. So you're going to have times 2x, which is essentially like the one we just did, right? And so this is going to give you 2x cosine x to the fourth. So now to find the second derivative, you just need to take the derivative of that, right? So this is just going back to basic derivatives using the product rule. I don't even think we need, oh, we do need the chain rule. But so first, I'll take the derivative of 2x. So I'll just get 2 cosine x to the fourth plus 2x. And then the derivative of cosine, is that positive or negative sign? Negative, right? Pretty sure it's negative. So negative sine of x to the fourth. And then what am I missing? It's the very last thing I need to include here. Yeah, I need to take the derivative of the inside of cosine, right? Or I guess sine now. And so I need to multiply this piece by 4x cubed. Yeah, and that's the chain rule again. And so you can simplify this a little bit, make it look a little bit nicer. So 2 cosine x to the fourth, and then minus 8x to the fourth sine x to the fourth. And so there's your answer. So any questions about the fundamental theorem of calculus, the first part of it, and using the chain rule with it? All right, so let's do one more example using this part of the fundamental theorem of calculus. There's a few questions on your homework like this. And so it's basically determining local mins and maxes, right? So it's combining this stuff with stuff we talked about in chapter 4. So here we're going to have capital Q of x is going to equal the integral from -1 to x of t squared plus 2t minus 3 all over 1 plus tangent squared of 5t, and that's all with respect to t. And then it asks, where does capital Q, so where does Q of x have a local min? So how do I figure out where a function has a local minimum? What do I do to it? It's the very first thing I need to do to it. Yeah, you need to find the derivative of that function, right? So we're gonna have to find Q prime. Yeah, and then the second step would be to find the critical points, right? And so you're gonna get Q prime of x. So when I do this, I'm getting the derivative of this integral, which that's a lot quicker. And so I'm gonna use the first part of the fundamental theorem of calculus. And so you're gonna get x squared plus 2x minus 3 over 1 plus tangent squared of 5x. So that's Q prime. And I don't have to worry about multiplying by the derivative of x because it's just 1, right? So even if I did try and use the chain rule, I would still get the same answer here. So this is my derivative. And then, yeah, the second step is to find the critical points of the function, which is where the derivative equals 0 and where it doesn't exist, right? So don't forget about that one. So here we need to find the critical points. So you're going to have where q prime of x equals 0. And then you're going to have where q prime of x does not exist. So one thing I want to point out is looking at, so we'll do the does not exist first. What do I normally have to do to figure out when a rational function doesn't exist? What do I do to it? Yeah, you set the denominator equal to 0. And so you're going to have 1 plus tangent squared of 5x equals 0. Can this ever happen? Look at what I'm dealing with here, right? So I've got 1 plus a square. So what is this number always going to be? Since this, yeah, it's always going to be positive, right? Since this part is always positive every single time because of that square, when I add 1 to it, it's going to stay positive. And so even if I get 0 out of here, I'd still get positive 1, right? And so 0 is the smallest number I can have for tangent squared. Oh, I didn't mean to erase all of that. And so here, this can never happen. And so you just put never. And so yeah, all we have to worry about is when it's equal to 0. And so to figure out when a rational function is equal to 0, you just set the numerator equal to 0. And so here, this factors as, what is it, x minus 1, x plus 3. Yeah, okay, cool. And then so you get x is equal to 1 and x is equal to negative 3. And so now comes the point where we test around these. So you draw your number line, that's a straight line. And so you've got negative 3 and you've got positive 1. And so this is the one where you would go and you would start checking things, right? So you would probably test like f prime of negative 4, f prime of 0, f prime of 2, or something like that. But you can just trust me for now. You're going to get that this is positive, this is negative, and this is positive. So let's say you forgot the increasing decreasing test to find local min and local max. Like you don't remember if it's from positive to negative or negative to positive. Draw it out, right? So you're going to have, if I'm increasing, then my function's going to look like this. It's going to increase, right? And so if I go from increasing to decreasing, what is this? Is this a min or a max now? Yeah, it's a max. And so I know local min is when I go from decreasing to increasing, right? And so I know that I have a local min at x equals 1. So local min at x equals 1. On the exam, there was a question that said, find where they have local mins and local maxes and then plug it and then figure out like what the y value of that would be. A few people were getting some answers that were marked as wrong, and I didn't check and see if it was marking you wrong on like if your answer was actually wrong or not. But to answer that question, what you would do is you would now find, so this has a local min at x equals of, or like with y equaling f of 1, right? So where you would plug 1 in to your original equation, or up here. You don't know how to plug, oh wait, no. Yeah, you can't do that yet. Because we haven't learned the second part of the fundamental theorem of calculus, but we're going to right now. And so here you wouldn't be able to say what this is just yet, but that's how you would get it. So does anybody have any questions about local mins or maxes like this, or about the first part of the fundamental theorem of calculus? All right, so the second part of the fundamental theorem of calculus says, so fundamental theorem of calculus, part 2. This is the big part. This is the fundamental part of calculus. But so here, if you have, and so this is very important, if you have a function, so if little f is continuous, continuous on the closed interval from little a to little b, then the integral from a to b of f of x with respect to x is going to equal the antiderivative of f evaluated at b minus the same antiderivative of f evaluated at a. And so here you have to say where f, or capital F, is any antiderivative of little f. And so what we basically can do with this is we can evaluate definite integrals without drawing out the picture and calculating it like it's an area, right? And so this is going to open up a lot of things for us. Let me kind of show you through an example why this makes sense. So it's like it's not a proof, but it's a good explanation. It's from my old calculus teacher. But so to see this, let's let little f of x equal the velocity. So it's going to be the velocity at time x of an object, right? Then when I go and I look at, so if that's little f, then capital F of x is going to be the antiderivative of little f. Antiderivative of little f of x. But when you think about it, so when we were first learning derivatives and velocity and acceleration and position and all of that stuff, position is the derivative of which one? Position or acceleration? Or there's a third one, which we talked about, which is jerk, but that came later. So since it's the derivative of position, when I look at the antiderivative of velocity, that's also position, right? So here, instead of thinking about this as the antiderivative, we can think about this as the position of the object at time x So that takes care of kind of like this half over here where these capital F's are coming from. So let me explain how the integral is equal to that part now. So we know that the integral from a to b of f of x with respect to x is equal to the area under the curve. And so in this case, it's under the velocity curve, right? Because little f is velocity. And so if I were to kind of draw this out, then, so like I think I had done a little example like this last time too. So let's say here's my curve from A to B. then we talked about how the integral from A to B was the area under this curve. But if you think about it now in terms of position and velocity and all of that stuff, so this would represent the velocity. Oh, wait, no. Yeah, because this would be f of x. So this would represent the velocity, right? But then if I kind of look at the area under this curve, then what else can I kind of think about it? If I just look at the x-axis, what can I kind of determine from this point to this point? Like, what can I say this is equal to? So yeah, it's going to represent the change in position. So rather than thinking about it as the area under the curve of velocity, you can think about it as the distance traveled from time A to time B. But if I look at this sentence, which I'm about to star right here, with the fact that capital F of x is equal to the position at time x, then what we really have here is that the distance at time A is capital F of A, or here, so I should do B first, right, because we're doing subtraction. So the distance traveled is going to be capital F of B minus capital F of A. So do you guys have any questions about the second part of the fundamental theorem of calculus and why the integral from A to B of f of x dx is equal to the antiderivatives subtracted? Okay, so let's do some examples of this. So, example. The first one we're going to look at is the integral from 1 to 5 of x squared plus 1 dx. So here, what you're going to do is you're first going to find, so basically what this is saying, so here you have, this is going to be f of x. So we need to find the antiderivative of this piece right here. So what is the antiderivative of x squared? Yeah, it's going to be x cubed, and then you have to divide it by 3. That way, when you take the derivative of that, you get 3 over 3, right? So you're going to have x cubed divided by 3 for that first piece, and then what's the antiderivative of 1? Yeah, just x. And so, okay, so Simon, you forgot to divide that first piece by 3. So real quick, just in case you guys don't see it, when I take the derivative of just x cubed, so if I didn't have this 3 here, then when I bring this 3 down, I'm going to get 3x squared and not x squared. So I just need to make sure I multiply all of this by 3, right? But so yeah, any questions about that? I don't know if you just forgot it, Simon, or if you, yeah. Okay, yeah. But so this is the antiderivative now. So this is just the antiderivative with constant 0, right? Because remember, antiderivatives, you can have any constant that you want. So yeah, Phil, no. The reason for that is if I include the plus c, then when I do f of b minus f of a, I'm going to get c minus c. So we can leave it in for now, and then we'll see that it just goes away. You're not going to, I'll do it with this one, but for the next ones, I'm going to leave it off. But so here, this is going to be the antiderivative. So it's the most general antiderivative with that c right there. Now, this is the step that is crucial when it comes to using the second part of the fundamental theorem of calculus, because right now I've just found f prime of x. I haven't actually evaluated it at b or at a, right? So what you do here is, depending on your preference, so some people just put a straight line and they'll say, okay, I have to evaluate this at 1 and at 5 and then subtract. Some people, rather than putting a straight line, they'll put like a little, like a big square bracket like this, and then they'll still put 1 to 5. So you can either do that or you can do this one, but either way, you have to kind of specify what your limits are. So your limits essentially move from the integral to this part right here. But so let's do the evaluation part now. And so what you're gonna get is, here, let me bring it down here actually, because I'm not gonna have enough space. So I first evaluate this whole capital F of x at 5. And so I'm gonna have 5 cubed over 3 plus 5 plus c. And so this whole piece is f, capital F of 5. And then I'm gonna subtract, so put this kind of in parentheses. I'm gonna subtract that same thing, but evaluated at 1. And so I'm gonna get 1 cubed over 3 plus 1 plus c, where this piece now is, oops, capital F of 1. And so then when you do this, be careful, make sure that you are distributing that negative through to every piece here, right? And so what you're really getting is 5 cubed is 125. So you have 125 over 3 plus 5 plus c minus 1/3 minus 1 minus c. And then if you look, these c's are going to cancel. So that's why you don't need to include it, because that's going to happen every single time, right? So when you're doing definite integrals, and remember, definite integrals just means you have numbers here. Whenever you're doing definite integrals, you are not going to include the c. If you wanted to, just to kind of play it safe, you can, but it's not necessary, right? Because they're always going to cancel like that. But so when you evaluate this, when you get common denominators and everything, you're going to get 136 over 3. So are there any questions about this example or how to use the second part of the fundamental theorem of calculus? Okay, so for part B, let's look at the integral from 1 to 2 of 1 over x squared dx. Oops. How can I rewrite this so that it's going to be a little bit easier to work with? Because finding the antiderivative of 1 over x squared is slightly, yeah, right, rewriting it as a negative exponent. That way it's easier to work with and the power rule comes into play. And so you have x to the negative 2 dx. And so now you need to find the antiderivative of x to the negative 2. So I definitely know, so remember when you're doing antiderivatives using the power rule, you add, no, you subtract 1. Or do you add 1? Quick, go, add or subtract. Question now, because I think my answer key might be wrong. Yeah, you're gonna add 1. Yeah, which means my answer key is wrong. And so here you're gonna have x to the negative 1, but as soon as I take the derivative of x to the negative 1, so I'm gonna bring that negative down, so I'm gonna have negative x to the negative 2 power. But so what do I need to kind of include right here? What do I need to do to get rid of that negative, essentially? Yeah, you need to make what you started with negative. So I'm going to make this negative x to the negative 1. And so that's the antiderivative of that. And so I just need to evaluate this from 1 to 2. And so what you get here is you get right here. So let me write it out this way first. This is also equal to just the negative of 1 over x evaluated from 1 to 2. So you're going to get negative 1/2 minus negative 1 over 1, which is negative 1/2 plus 1, which is just 1/2. So any questions about this example? So part C, we're going to have, oh, black screen still. So for part C, we're going to have the integral from pi over 2 to 2 pi of cosine of theta with respect to theta. So here, let me move this down a little bit because I don't need that space. But here, so cosine of theta is going to be our antiderivative, or is going to be our function. So we're going to need to find the antiderivative of cosine. So what is the antiderivative of cosine? Positive or negative sign? Yeah, it's positive sign, right? So we're going to have the antiderivative of this is sine of theta. And then I'm going to evaluate that from pi over 2 to 2 pi. And so you're just going to have sine of 2 pi minus sine of pi over 2. What is sine of 2 pi? You guys remember? Try picturing your, yeah, it's 0, right? So you're going to have 0 minus, and what's the sine of pi? Yeah, that's 1. So remember, if you are better with degrees, this is the sine of like 360 or 0, and this is the sine of 90 degrees, right? But technically, when you talk about the unit circle, I want to say it's specific to radians. Like when you derive it, it's based on radians. But yeah, so your answer here is -1. All right, so let's do one more like this, and then we'll do another type of example. So part D, we're going to look at the integral from ln of 3 to the ln of 6 of 8e to the x dx. So real quick, what can I do with this constant right here? What am I allowed to do with it? Yeah, you can bring it out front. And so you're gonna be able to skip this step. I'm just gonna do it kind of slowly for right now. But you don't have to do this. You can just have f of x equal to e to the x. And then what's the antiderivative of e to the x? Think about what you need to differentiate to get e to the x. Yeah, it's just e to the x, right? And so here, you're going to have 8 e to the x evaluated from ln of 3 to ln of 6. And so here, real quick, let me just kind of write this out. So if little f of x is equal to e to the x, then so is capital F of x, right? But okay, so black. Here, you're going to have 8e ln of 6 minus 8 times e, oh, to the power of ln of 6, not times. Whoops. minus 8e to the power ln 3. What happens to the e ln of x? Like, what is e to the power of ln of x equal to? Yeah, it's equal to x. And so what I'm really getting here is 6 and 3, right? So you have 8 times 6 minus 8 times 3, which is 48 minus 24, which is 24. Okay, so we just did 4 integrals using the second part of the fundamental theorem of calculus. So do you guys have any questions about how to solve these? Okay, so for this example, you're gonna have, so before I give you the function, what is wrong with the following argument? All right, so I'm just gonna kind of write down a problem, like, and solve it. And then I kind of want you to figure out where I went wrong. So if I look at the integral from -1 to +1 of 3 over t to the 4th dt, when I do this, I'm gonna rewrite this as 3t to the -4 dt, so it's easier to work with. When you take the antiderivative of that, you're gonna get 3t to the -3. Then you have to divide by -3 to get rid of the -3 that comes down. And then this 3 just kind of goes along for the ride. And so you're going to evaluate this from 1 to -1. And so when you do this, I can also just cancel these t's. So this is going to be t to the -3 over -1, or just negative t to the -3. I'm going to evaluate that from -1 to +1. And so what I'm getting here is -1 to the -3 power minus -1 to the -3 power. And so here you're getting -1 over 1 minus 1 over -1. -1 plus 1 is 0. Wait, I think I did something wrong there that I didn't mean to do wrong. Let me just write this as 1 over t cubed. I've already made the mistake, so start looking for it. See if you can catch what I've done wrong. So yeah, the issue is that you can only use the second part of the fundamental theorem of calculus if your function f of x is continuous on your interval from a to b, so from -1 to +1. So since f of x equaling 3 over t to the 4th is not continuous on this interval, we are not allowed to use the second part of the fundamental theorem of calculus. So we are not allowed to use the FTOC part 2.